А то, что там ничего не отображается, это нормально?
Да, тут экран тоже надо включить. Можно включить. Сейчас мы просто надо включить.
Можно его включить?
Вот там.
Ты. Okay, I'm sorry. This time I will try to use new blackboard. I hope that this will be okay. So, what we did last time? Last time we defined neuron severity group of a variety, and we proved that for a K3 surface we have an isomorphism of neuron severity group of X with the Picard group of X for K3 surface. Yes, we proved that Picard group of X doesn't have any torsion. And also we computed a Hodge diamond of X. This is the following thing. Hodge diamond. We computed it for complex K3 surface, but in fact it works for all K3 surfaces in all characteristics. Okay, and now
Нет, просто это закрыть надо большую, если мы не пользуемся.
что?
Ну, у тебя открыты две доски просто, да, вот, когда ты пишешь. А то лучше закрыть, наверное.
Что закрыть? Как мне открыть? Okay, and yes, currently is that Picard rank of a K3 surface is less or equal to 20. So this corollary is just a consequence of Lefschetz 1-1 theorem. From Lefschetz 1-1 theorem that tells you that if you have a Picard group of a variety, then it surjectively maps to an intersection of its 1-1 homology with its integral cohomology. So, and as far we discussed exponential sequence, we can immediately deduce this Lefschetz 1-1 theorem. So last time,
Why does it follow from? Why does it follow from Lefschetz theorem?
because last time we why this follows from Lefschetz? Because last time we have computed that rank that H11 is equal to 20.
Yes.
And we know that our Picard group, сейчас. Что мне сделать, чтобы здесь была доска?
Тоже ее открыть. Вот.
Ну, я пытаюсь, но не открывается. Она не открывается. А как другая доска называется? Ладно, I will use this one. Okay. Let me first explain why we have Lefschetz 1-1 theorem, and then I will explain why rho x is less or equal to 20. Okay. So last time we discussed exponential exact sequence that tells you that Picard group is mapped is mapped to second cohomology with integer coefficients by first Chern class, and then it's mapped to and in fact this map goes through the embedding to second cohomology with integer coefficients. And here, let me remind that we have Hodge decomposition that tells you what? That tells you that here we have H2, maybe как ластик сделать? Стандартный. Окей. That tells you that this is decomposed as H0, H11, and H02, right? And that these two spaces are conjugated, are complex subspaces that conjugated to each other. Okay? So we see that the image of Picard group. And we see, of course, that this subspace inside this is a real subspace, right? Just because this is with integer coefficients. So if we have some part here, then we also should have some part, non-trivial part here, then we also should have some non-trivial part here, just because this is a real subspace. And you see that this surjective map is just the corresponding projection to one of the component. Okay, so we immediately obtain the Lefschetz 1-1 theorem from this exact sequence. Okay, so its map it is mapped here to 0, the image of Picard, just because this is an exact sequence.
Why couldn't there be any image in the H20?
Just because this is a real subspace. And these two complex subspaces are conjugated to each other. This is a property of a Hodge decomposition. So if we will have some non-trivial, so if it has trivial part here, then a real subspace should have trivial part also here, just because they are conjugated to each other. These two subspaces complex. Okay? Is it clear?
Please, what is the map from H2YC to H2YOS?
Just projection. So we have a direct sum decomposition. This is a Hodge theory.
Right.
And the property of this decomposition is that these two subspaces are conjugated to each other. Okay? And so this map is just the projection.
But
So
then,
this is H. Okay? You see? Sorry, let me maybe remind that I denote by
Yes.
K. Omega So what?
Just a little bit confused. They are conjugate to each other, but they don't have any intersection. So
But I mean, this is a real subspace. This is a real subspace. So okay, you can just I can leave this as an exercise. So this whole this follows from Hodge theory and from the corresponding decomposition. Okay, and now what? Okay, and now how we can? Yes, and maybe I should say that in fact. For those one who knows, that for in fact, if we have an algebraic cycle of codimension E, algebraic cycle of codimension I, then it has a class. A class in second in this cohomology, and if we consider the corresponding embedding, then the image of class of this class will lie always in I component of the corresponding Hodge decomposition. Okay. So for all algebraic cycles, we always live in this part. Okay? We don't have surjectivity in general, but all algebraic cycles live in I components. And for divisors, the story is especially nice. Okay, and что происходит?
Это задержка.
Хорошо, спасибо. Okay, and now how we can obtain that the rank is less or equal to 20. We know that our Picard group of X lies inside H11X intersect with H2X. Yes, and last time we computed rank of this thing, so this is 20, right? So the rank of the Picard group is less or equal to 20, okay? So last time we computed this. Let me remind that this is H11. Okay? Is it clear? Just because we can't.
Why this arrow is eidetic?
Just because this is was a consequence of for this holds for K3 surfaces. Here, for K3 surfaces, we have an embedding, just for K3 surfaces. Okay?
But by the Lefschetz theorem, it's a surjection.
Yes. So this is isomorphism.
So rank is exactly.
No. Because we have an intersection here with integer.
Oh, yes.
Okay. So, and I should say that all. Every Picard number. Every Picard number between 0. So for non-algebraic K3 surface, we can have 0 Picard rank and 20 is realized by some K3 by a K3 surface. So here we can have all possibilities for Picard numbers.
it was building because there's no torsion and because
We discussed this last time, just from an exponential exact sequence. You immediately obtain that for K3 surface, this is immediate. But here was an arbitrary one, so let me write it here like this. Okay, and now yes. And now let me give you exercise that in fact a K3 surface with picar rank 20 is quite easier to construct. So consider just Fermat quartic. This is a quartic inside E3 that is given by a very easy equation. So we have already seen that this is a K3 surface on our first lecture, and an exercise is to show that the picar rank is in fact 20. So how you can show this? So first of all, try to construct around 48 lines on X4, and then from this deduce that the picar rank of X is at least 20. And as far as we know that this is a K3 surface, we know that this is 20. Okay, it's maybe not it's not a very easy exercise, but it's nice, and you can just try to do this for fun. Тебе MZ. Okay.
Yeah, I have a question. And so every picar number between 0 and 20 realized by some K3 surface.
By some, yes.
Yes, but if we restrict to projective K3 surface.
Then at least one, because we always have an ample line bundle on a projective K3 surface. So 0, on a projective K3 surface, we always have
a number between from 1
yes,
to
for
20
projective,
realized.
yes, for projective, every picar number between 1 and 20 is realized. And here is an example that this, that our оценка, our estimate is optimal, so it's very easy to construct an example of K3 surface that has picar rank 20. Okay, it's not so obvious to prove this, but maybe try to use some group action. You see, it's very symmetric. Okay, and what next? Yes, and now let me. Ой.
Легче его страницу сделать.
А как?
Ну там
Вот
зелё-
это?
Нет, нет, нет. Правее.
Вот это?
Такая страничка с
Вот это?
зеленым плюсиком. Нет, нет.
Вот это. Вот это. Окей. Спасибо. And now let me prove the following proposition. For a complex K3 surface, its cohomology is a free abelian group of rank Ks. This is the sum of H QS.
S is also a K3 surface.
Yes, yes. For complex K3 surface. So here, just because we consider this cohomology, we need to consider complex surface over complex numbers, right? Because otherwise we don't have singular cohomology. Of rank equal to 1, 0, 22. This is for k equal to 0, for k equal to 4. This is for k equal to 0 or k equal to 3. This is. So we have already computed this part because we just compute Hodge diamond of a complex K3 surface, but we still need to prove that this is a free abelian group. And this is just a consequence of Poincare duality. So first of all, let me remind that we, on our second lecture, or maybe on first, I don't remember, we have proved that there are no unramified covers. Unramified covers of finite degree. And from this we immediately obtain that first cohomology of S vanishing. Okay? Otherwise, we would have a quotient, a finite quotient of the P1 of the fundamental group. And now we know that 0 cohomology is just that. So we can use universal coefficient theorem. Universal coefficient theorem will give you what? That our cohomologies is isomorphic to homologies mapping to Z plus x1 Что происходит? Можно спросить? Сейчас. I'm sorry. And now here we have hk minus 1 as z maps to z.
What's written of H?
1 minute, please, and I will show you what is written. Что делать? Кто-нибудь помогите мне. Почему это происходит?
Я выучу, кто помочь мне.
Я знала, что с этой доской будут проблемы. Саш, позвони, пожалуйста, Гоше, да?
Ага. Нет, вообще у тебя есть опция просто продолжить писать на левой, а на этой просто новую страницу начать. Я думаю, новая страница не будет быть.
Да? Угу. То есть это
Ну,
вот
если
сюда.
ты ее начнешь, то она сотрется все. То есть верни назад желтую стрелочку.
Как?
Желтую стрелочку. Вот, ты можешь рассуждение на левой доске дописать, а потом
Ну,
просто-
мне просто, я уже выписала эту формулу, не хочу ее писать по 5 раз. Ну ладно. Да ладно, видимо, я хочу ее писать по 5 раз.
I think we should ask for blackboards back.
А?
I think we should ask for blackboards back.
Вот.
То есть вот что с этой происходит, да? Если ты на нее нажимаешь, ничего не происходит. На синенькую, в смысле.
Ну, ничего не происходит, да. Я пыталась, потому что с этой доской я умею работать, но она просто не открывается.
Слева все пропало.
Слева все.
Но там ничего не было.
Ну,
такого.
нет, там ничего не было, но сейчас, может быть, если я нажму. Вот.
Сейчас. А может быть, можно вот так перетащить пальцем слева направо?
Вернуть. Не вернется.
Юля, попробуй. А вот слева, если ты нажмешь вот на верхнюю плашку и направо ее потащишь, она перетащится.
Что, вот это?
Да, вот так и направо. А на другой экран не перелезть?
Зачем нам это?
Ну, потому что там вторая есть еще. Она вторая, вот которая справа синенькая, она открывается во втором окне слева.
Да?
Да.
Ну да, обычно, когда на втором уровне переносят. Check.
Maybe we can ask for a room with whiteboard or blackboard because they have some empty rooms.
Ладно.
But
я
it's next
не-
time, maybe.
What?
Maybe next time we can ask for some room with blackboard or whiteboard.
Okay. Okay, let me write it here. The invert. Let's write it one more time. Z is isomorphic to and so we immediately obtain from this formula that for k less or equal to 2, hk and z doesn't have any torsion. Right? Just because the first, the zero cohomology is just set, and the first are vanishing. And now, from Poincare duality, that tells you that H SF is isomorphic to from 2n minus q and z plus x to 1 h2 n plus 1 minus k as z. From this we immediately obtain that hk as z doesn't have torsion, for k greater or equal to 3. Okay, so this is just a consequence of Poincare duality and universal coefficients theorem. Okay, and now let me also describe what is in fact the corresponding lattice H2 as Z. Let us describe H2 as Z with the intersection form. Intersection form. We know that this is torsion free, that its rank is 22, and now we want to describe explicitly intersection form. So we want to describe the corresponding lattice. Let me remind some basic notions about lattices first. So what is a lattice? This is just a free Z model, a free model of finite rank with symmetric bilinear form. Bilinear we will always suggest that this form is non-degenerate. So this is a map from the lattice to that. We say that this lattice is even when self-intersection of every element of this lattice belongs to even numbers. Yes, and I already say that we suppose that this form is non-degenerate. Is non-degenerate. Okay. Yes, and what is the corresponding signature? So if we consider the corresponding R linear extension, then this form can be diagonalized. With 1 or minus 1 on the diagonal. And the signature of is the number of the corresponding plus 1 and minus 1. Oops. Where and plus minus is the number of plus minus 1 on the diagonal. Okay, and index of the lattice is the difference between n plus and n minus. And also, okay, we can consider that the determinant of the intersection form, and we will say that lattice is unimodular if this is called discriminant if its discriminant is equal to plus or minus 1. Okay? So
What
is
is
it
determinant?
determinant is determinant of the corresponding intersection form. So we just, I mean, for an intersection form, we can write down a matrix, the corresponding matrix, right? Gram matrix, right? And we can compute its determinant, and this is what is called discriminant of the corresponding lattice. Okay, and we say that the lattice is unimodular if this discriminant is equal to plus or minus 1. Okay, and now let us consider two examples that we will need. Examples. So the very first example is the hyperbolic plane. That is two-dimensional lattice with the intersection form this. So what does it mean? This means that U is a direct sum of two copies of Z with quadratic form given by equal to f quadratic equal to 0 and intersection of E f is equal to 1. Okay? And the second lattice is a bit more subtle because this is a Cartan matrix, in fact, of an exceptional Lie group E8. But in any case, you can write it down. E8 lattice. So intersection matrix. I want to write it down just at once, just because I don't want this notation to be a black box. Okay, so I will write it down, and maybe if you will do some representation theory, you will need this matrix again. It's a Cartan matrix of the Lie algebra, of the exceptional Lie algebra E8. So what is the corresponding matrix? Okay. So the lattice associated to the Dynkin diagram EA. Okay. And also, let me also write that for any lattice, we can consider it twist. This is by definition the following thing. So as a Z module, the twist just coincide with a lattice as Z module, and the intersection form on the twisted lattice is just M times intersection form on the lattice lambda. Okay?
What is the twist by M?
So twist by M is this means that we just take intersection form of our lattice and times M. So we just rescale it by M.
Okay.
Okay? Yes, and also let me state ладно, это была плохая мысль пытаться это сделать. And also let me state that for two lattices, lambda 1 and lambda 2, we can consider their orthogonal direct sum. Direct sum. That is a direct sum of the corresponding Z models, and the intersection form is the following one.
With one question, should that be M squared for the scaling?
We will, okay, today we will need just -1, so, okay, today we will just use this. But we can consider this for any M.
Yeah, I mean the coefficient for the inner product for the bilinear form should be rescaled to M to the power should be M squared, right? Because you rescale
So we just rescale our matrix by M, our matrix, our Gram matrix. Okay, so, and this is this is what? This is x1 plus 2 equal to 2. Okay, and now we are ready to state lemma. Lemma. In fact, this is a topological lemma, so we will prove it using some terms from topology, but in any case, I should formulate it. So we have our lattice, the second cohomology of a K3 surface, and this is an even unimodular lattice, non-degenerate lattice of signature 390 that is isomorphic to the following direct sum. This is an E8 twisted by -1, and here we have 3 copies of hyperbolic plane. Okay? And how to prove this? Proof. So first, non-degeneracy and unimodularity follows just from Poincare duality. Follows from Poincare duality. Duality. Then the fact that it's even follows from so-called Wu formula. This from topology, of course. This formula tells you that if you have a class in second cohomologies, then this is the same thing as canonical class L modulo 2. So for K3 surface, we immediately obtain that because our canonical class is trivial, we immediately obtain that the intersection form is even. And now this thing follows from Hirzebruch index theorem. Hirzebruch index theorem that tells you that the difference between numbers of +1 and -1 is equal to canonical class in self-intersection of canonical class minus 2 Euler characteristic of S C divided by 3. And this is equal to what? Minus 16. Okay, and on the other hand, we know that this sum is equal to 22. So we obtain that the signature is the first one. And this result follows from classification of lattices. So knowing, if we know that this is even unimodular non-degenerate lattice with this signature, it is possible, it's not obvious at all, to prove that this lattice will be isomorphic to this sum. Okay? And okay, this is so now we computed some invariance of a complex K3 surface. And now let me start a new theme about linear systems. So before we will prove.
Wo formula works for only surface.
Yes, for surfaces. Now let us discuss something about linear systems on K3 surfaces, because I think this is an important subject.
Excuse me, I don't understand. So, K parent with K is 0, right?
Yes.
So we obtain 32, and we divide it by 3.
Wait.
It's topological, right?
Minus 2. Topological. So, okay, this is an exercise, okay, for those one who understand me. For just proving from this formula that we have a minus 60 and using what we already proved before. Okay. Linear systems. This is a topological. This is an alternating sum of integer cohomologies. Okay, and linear systems. So first, let me remind that if we have a smooth complex variety, a smooth variety, I think that here we can also consider not complex but over algebraically closed fields everything. But for simplicity, let me use this assumption. So, and we have a line bundle on X. Line bundle on X. Then linear system that is associated to this line bundle, this is just a factorization of global sections of L. Or equivalently, this is just the space of all effective divisors. Of all effective divisors D in X, linearly equivalent to L.
I believe you need also projective assumption here.
Yes, okay. No, we don't need, it's, we can define line bundles on any analytic space, and we can consider all the corresponding divisors linearly equivalent to. We need projectivity assumption we will need when we will consider ample line bundles. For the existence of an ample line bundle, we will need this. But the whole story with linear systems and corresponding morphisms to projective spaces, it holds for any complex variety. Okay? And now, yes, and now we can define base locus of L just as an intersection of divisors from these linear systems. For all global sections of X. Yeah? Or equivalently, this is a maximal closed subset that is contained in all effective divisors from this linear system. Okay? And now, if we have a line bundle, then, and if this line bundle has more than one section, then it induces the amorphism rational map from X to the projectivization of the dual global section rational map. And this map is irregular on the complement of base locus of L. So, informally speaking, what is the corresponding map? If we take a point here, we just consider what divisors vanishing on this point F, and if this point is not in the base, doesn't lie in the base locus of L, then this is a hyperplane in the global sections. So, and this gives you a point in the corresponding projective space. Okay, and now, yes, for x for a surface x, the base locus can have components of dimension 1 or 0. Can have components of dimension 1 or 0. And we will call the fixed part of L of linear system one-dimensional part of its base locus. So if F is a fixed part, then we immediately see that global sections of the corresponding effective divisors is what? What is the dimension? Everyone understand why the fixed part is rigid? No? So suppose that it's not rigid, right? Then F is linearly equivalent to some other divisor F0. What we know about L? We know that all divisors in L, they are just direct sum of F plus D, right? Just because this is a fixed part. And now, if it's not rigid, if there exists some effective divisor that is linearly equivalent to F, then this is linearly equivalent to this thing. And this thing already doesn't contain F. This is a contradiction. So all divisors in the fixed part of linear system should be rigid. Okay, we can move them. And and now we have a natural embedding, and for fixed part, this induces an isomorphism of the corresponding global sections. X, L, minus F. It is a more.
Sorry, I don't understand this embedding. This is a large bundle.
Oh, sorry. Okay, then it induces an isomorphisms of global sections, just because this is divisors that are effective on F, and this is a fixed part, so all line bundles from L have F as this part, so this is an isomorphism. And note that the corresponding morphism on that is defined by the linear system L on the complement to the base locus is identified with L minus F. And morphism to projective space that is defined by linear system L minus F already induce a morphism on X without finite sets of points. Is a finite set of base points of L minus F, and this set contains the zero-dimensional base locus. So what I wrote here is just trivial. I just wanted to write this down. So this linear system already doesn't have one-dimensional base locus, right? And this the induced morphism is identified. The induced morphism can be identified with the morphism of phi L on the complement to the base locus, and base points of this linear system. We still can have some base points, but it's just points. It doesn't have one-dimensional part. And this base points contains the base points on the linear system L. Okay, and now let me. Okay, and also for a linear system, we will define the mobile part of L. This is by definition is this L minus F, and note that first M is numerically effective, and then note that the mobile part intersect all closed curves. All closed curves C and X as something positive. Is this clear that mobile part is NF and this intersect? Okay. And now let me state maybe in the okay. Let me state what is what we will have for K3 surface with linear systems. So what we have discussed so far about
Sorry,
linear systems is
I
just.
don't understand why these different two things.
Oh no. No. Sorry. This is NF, right? And this is greater or equal to 0 for M. These two properties first and this. Sorry. Is this clear? These two things. Now, what we have for K3 surfaces? the fixed part.
Actually, F divisor should have self-intersection larger or equal than 0, so
But
because you can write it
yes, yes,
as
right.
minus
Mhm.
something very small.
Yes, this just follows. Okay, so let me write this in this way. The fixed part of any line bundle on a K surface is a linear combination of rational curves. Where Ci are just E1 and Ay is greater or equal to 0. So why this is so? So if we have a line bundle on a K3 surface, then its fixed part is always a linear combination of rational curves.
Are they always smooth rational curves? Or
Yes, yes, we will discuss this now. And in fact, before proving this, let me remind what is an arithmetic genus, maybe. So for all possibly singular non-reduced, reducible curves, curves. C. Что это было?
Видимо, доска закрылась.
Ладно. Ну ладно. So for all curves, we can define its arithmetic genus as just difference between one and other characteristic of its structure sheet. Let me recall that before we define genus, just the first dimension of the first homology, but we did this for irreducible curves. For irreducible curves, of course, arithmetic genus is equal to the dimension of the first homology, right? But here, the point is that we can arithmetic genus we can consider for all curves. It doesn't matter how singular they are, for arithmetic genus, we have just the same formula as we proved before, and we can prove it exactly in the same way as before, that this is equal to intersection of C, Kx plus C. So for K3 surface, for a K3 surface, we have is equal to the self-intersection of C. Okay, for all curves. And now, note that for integral curves, we always, its arithmetic genus is what?
Just geometric genus.
No, I don't suppose that it's smooth
Integral?
for integral curve. So it's always greater or equal to 0, right? And now,
But for the definition, you also don't require it to be smooth. You just require it to be reducible, right?
right? No. For definition of arithmetic genus, it doesn't require anything. It can be.
Yeah, I mean for the geometric genus.
Here, yes, I said that when I prove this formula, I use this definition and I use just this curve should be irreducible.
Okay.
It can be singular. But we now discuss some particular cases. So for integral curves, we always have this inequality, right? Just because for integral curves, this is equal to h1.
Yes.
Mhm. And so for an integral curve on K3 surface, what can we say about its self-intersection? Is great from this formula.
Greater or equal than -1.
Mm-hmm. And
-2, I'm sorry.
-2. Yes, and in fact, curves with the self-intersection -2 will play will play special role in the whole story. So let me give a definition that a -2 curve on a K3 surface is an irreducible. We suppose that it's irreducible curve with self-intersection that is equal to -2. Okay? And now,
So do we need the information that this is K3 surface? Or can we give...
to prove the
No, in definition.
in definition, no. But what we will state now, we will need. Okay. No, first of all, note that it's integral, right? So if it's -2 curves, then it should be integral, right? Just because if it's some A1C is equal to A1. So and A1 should be 1. And moreover, the most important thing is that it is smooth. Here we don't need that the corresponding here. What I will prove now is that if a curve has an arithmetic genus equal to 0, then it is smooth. So for this statement, we don't need a surface to be K3 surface. But here I need that this. But here I used not an arithmetic genus. I used self-intersection, and we know that for K3 surface, self-intersection -2 implies that arithmetic genus is equal to 0. Okay. So what I'm saying is. What I will prove now is that if arithmetic genus is 0, then it's smooth. Okay, indeed. Let's consider its normalization. Its normalization. And now we will have an exact sequence. OC maps to what?
Push forward of structure.
And here here what we will have some kernel that is concentrated where?
Some
In single points.
Mm-hmm. So this is concentrated in singular points of C. Yes, what does it mean? This means that it's first cohomology what?
0.
Vanishing, and its first cohomology is just some direct sum of vector spaces that are concentrated in singular points, right? And now what we have from this exact sequence? From this exact sequence, we will obtain that arithmetic genus of C is equal to what?
Genus of C tilde.
Plus what?
Plus dimension of global sections.
Plus dimensions of the corresponding vector spaces, right? And this is something that is concentrated in singular points of C, right? So what we see from this formula? We see from this formula that if we take a normalization of curve, then its arithmetic genus will be less than arithmetic genus of C. So NA of C is is greater than arithmetic genus of C tilde. And now we know that for an irreducible curve, our arithmetic genus is 0, right? So we don't have any normalization of this curve, right? So from this, we immediately obtain that if arithmetic genus of C is vanishing, then it is smooth. And moreover, in this case, arithmetic genus is just a geometric genus. And what is geometric genus? So it's 0, and this means that our curve is P1, right? So this is just P1. Smooth. This means that C is isomorphic to P1. Okay, and now how we can prove lemma. This is the last thing that I will explain, and we will stop. Lemma. About fixed part, that this is a linear combination of P1. So what we know about fixed part? We know that their global sections are equal to 1. So if we have an irreducible divisor here, then its global section will be also what? 1. It will be also rigid. And now also from this, we also immediately see that by shear duality that this is equal to 0, right? And now if we consider the corresponding Ой, не то. The corresponding Euler characteristic
So we apply C duality to the fact that C is effective. So it's
yes. So this is 2O and minus C, and so this is 0. Okay, this doesn't have any global sections. So, and now if we consider, or maybe it's better to write this OC in this way, then it will be equal to what? And this means this will be equal to 0 on the one hand, and this will so from this we obtain that the self-intersection of C with itself is -2. Okay?
It's -4 in this one.
Where? What? -2?
Two.
Oh, no. Сейчас.
So the Euler characteristic y is 0, it's at most 1. We can always say.
Что-то я не то написала сейчас. Секунду.
There should be 1 plus.
1 plus, yes. One. Нет, сейчас, секунду.
One minus second.
Y minus. So first of all, we need to 1 minus 2, and this will be equal to C times C minus 2. C times C plus 2. Okay? Then we will obtain that the self-intersection of C with itself is -2, and from this and what we have done before, we see that C is isomorphic to pi1, and this is an effective divisor, and so F is an effective divisor that is a linear combination of P1. Okay? Sorry for this.